Hey everyone, we are back to the agricultural drain model, part 3. So we've had a couple of exercises with various iterations of this model of a farm with a drain on the east and the west side. And in this case study, we are going to do something very simple. We're just going to add a pond in the middle of the farm, and we are going to simulate the leakage between the pond and the aquifer using the general head boundary package. So there will be a conductance representing the sediments at the bottom of the pond that we'll simulate. And so we are going to start with a completed version of our second iteration of this, the 6-layer model from part 2. And in the instructions, it has you download a zip archive and then read that in. So I've already downloaded that and unzipped it. So I'm just going to go into GMS now, and it is AgDrains 2. And I'm going to, it's zoomed out a little bit for some reason, so I'm going to click on the frame image tool to have that expand to fill the screen. And then you notice in the Project Explorer window how these there's a set of CAD files that hung around from a previous solution, and then this 3D grid data. And you can expand those individually, but there's also a little shortcut I'll show you. If you right-click on the project window and select that project symbol at the very top of that hierarchy and select Expand All, it just opens up every item and each of the sub-items in that list. So let's look at what we have here. It kept around one of our CAD files. I don't think we'll need that necessarily, but so I'll turn that off. And what we're going to do is I'm going to use the Select Cell tool. And I'm just going to kind of randomly select a region somewhere here in the middle of the model. And let's say, just for the sake of argument, that the farmer that operates this property decides to put in an irrigation pond, and maybe there's some kind of liner at the bottom of the pond, a clay liner or something, or just some compacted materials that separates it from the aquifer system, or the water table, or the materials underneath the pond. So we could represent that using the general head boundary package, which is a really common package to use for simulating lakes and ponds and sometimes rivers as well. It's just a very simple head-dependent boundary condition. It's very similar to a specified head boundary condition. In fact, if you use a very large value of conductance, it becomes identical to a specified head boundary condition. And unlike the drain package, it goes both ways. It can be both a source and a sink. So just a very simple package to add on here to simulate external sources and sinks like an irrigation pond. So I'm going to right-click on that, select Sources and Sinks, and we will select GHB for General Head Boundary. And we're going to do Add BC. And as per the instructions, go back to the instructions. It says let the elevation equal 3830, so that would represent like the stage of the water in the pond, and use a large value for conductance, 1e to the 6th. And so let's give that a shot. So we'll say 3830, and I'll tab over, and then 1e to the 6th. Again, whatever we enter in this top row gets copied down to the other cells. And so we click OK, and there are the symbols there representing that we've assigned general head boundary conditions to that particular set of cells. So let's before we run this model, let's look at our current flow budget. So we have 32,000 or 33,000 feet or cubic feet per day coming into the model. And let's see, that should be balanced going out. Let me see, try that again. No, it's not. There's about a 1% difference. It surprised me. That's a little larger than you normally see, about 382 cubic feet per second. Yeah, pretty close, but we'll run that again, see if we get a more balanced budget. But it's really simple. What's coming in as recharge is going out to the left and right boundaries. And so let's save that. And whoops, let's see. We want to save this as Ag Drains 3. We'll give it a new name here. And then we'll run mod flow. And notice it takes a little longer to converge this time. We got up to 82 time steps. It's still pretty quick. And so what happens here is we have a lower water table than we had before. So actually what I should have done is looked at the water table elevations. Let me see if I can read the solution from that previous one, Ag Drains 2. So here's the solution from the Ag Drains 2 model. You can read in the solution without exactly reloading the model. And so the simulated head value is at 3831. And so, and I'm going to switch to the, and remember, we put these general head boundary conditions in here at 3830. So we put the stage in the pond a little bit below what the normal water table would be. And so therefore this pond is going to become a sink. It's going to become a place where water goes from the aquifer into the pond. And if the elevation of water in the pond was above the ambient water table conditions, then water would go the other way. It would be a source of water, but it's going to be a sink here. So let's go back to our solution, and you'll see that within within the pond, if you look down at the bottom, as I move the cursor, you'll see that the head is almost exactly 3830. And if we look at the flow budget, let's see what the flow budget says. So we have, 33,000 coming in, and we have 30,000 going out the drains and about 1,800. So we're actually got a surprisingly big discrepancy here in our flow budget, about what, a 2-3% difference. That seems a little high to me. We might want to try. Let's look at what. Oh, we're using the SIP solver. Aha! Well, that explains everything. Let's go in and change that solver. This is what I imported a minute ago. Let's change it to the PCG solver, and then save and run that again. And let's see what kind of. Well, we get a little bit different solution here. Flow budget. Oh, there we go. It's well, it's still it's still about a 2% difference. It's higher than I would normally expect, but we could play with our solver differences and see if we could figure that out. Let me see if that converged. Nope. Let's see. Cancel. Let's run that one more time. I just want to look at the convergence. Yeah, conversion 4 iterations. So, well, we'll call that close enough. But the point is, of the flow budget now, we have water. Part of our water is going out the drains, and part of it is going into this irrigation pond through the general head boundary package. A negative sign means it's going from the aquifer into the irrigation pond. So that's what we got with a conductance of 1e to the 6th, which is really large. Let's go back to the instructions, and it says compute a conductance assuming the pond is lined with a K equals 0.01 foot per day material with thickness equals 1 foot. Save and run. So we need to, from that, we need to calculate a conductance. So I'm going to launch Excel here. We'll do some conductance calculations really quickly. And let me fit that to my window. Whoops, there we go. And so here we have a K value equal to 0.1 feet per day. Whoops, I said it should be 0.01 feet per day, misspelled that. And remember, the conductance is equal to Ka over L, right? And so we have K, so what is the area? The cells are 50 feet by 50 feet, so it's going to be 50 times 50 is the area. And then L, the length of flow, is 1 foot. Let's put some units here. Foot squared. All right, and so the conductance, CD we'll call it, is equal to K times A over L. And we get 25. That actually works out to feet squared per day, the units of our conductance. So going back to GMS, if we go into the, we can select, whoops, excuse me, we can select these cells. Having trouble selecting them here. I'm going to drag a box right there, right click and say, let's change the conductance to 25. Okay. Another way to do that is we could go to the ModFlow menu, optional packages, drain, and edit the values right here. Either way works. So save your changes, run the solution, converges right away. And you'll notice that the contours look different. And if you move the cursor, it's still about 30. Well, before, when I moved the cursor around these cells, it was almost exactly 3830. Now it's 3830.9, 3830.8. So it's not exactly 3830, meaning before we had a super high value of conductance, so it acted almost exactly like a specified head boundary condition where the head of that cell would be precisely what you specified. Well, now it's a little different because there's some head loss as you go between the aquifer and this external general head object. And obviously a conductance of 25 is more orders of magnitude less than 1 e to the 6th. And so let's see what that did to our flow budget. So before we had about 1,800 feet going into the general head boundary condition. Now we have 1,272. Now, interestingly, look at our percentage difference on our head loss down here, or excuse me, on our flow budget down here. And in my experience, we had like a 2 or 3% error before, and I think when you use a really big value of conductance like we did before, it leads to some numerical instabilities, which can sometimes cause that flow budget to be off a little bit. And really, you don't normally enter a conductance of 1 e to the 6th. If you want an infinite conductance, you use a specified head boundary condition. And so that's an extreme case. I can't think of any reason why you'd ever do that in practice. So that's not normally a problem you run into. But we're doing it in this case just to show you how the conductance impacts the solution. But it's going from 1 million down to 25. We caused the flow budget to go from 1,800 to 1,200. So the amount of water flowing through there is not as sensitive to the conductance as you might imagine. For example, if we were to continue to reduce the conductance down to an even lower value, at some point that general head boundary condition that represents that pond would have a pretty minimal impact on the head values. So let's illustrate that. This is not part of the instructions for this exercise, but let's do it anyway. I'm going to go into the general head boundary package, and I'm going to change the conductance from 25 down to 2. So I'm going to enter it there and double click that little rectangle to copy that down, and we'll save that and run it again. And now you can see almost no change. You can see a little bit of a wiggle in the contours, so there's a slight impact, but nothing like we had before. It's almost as if the pond doesn't exist. And if we go into the flow budget, you'll see now we're all the way down to 186 cubic feet per second going out. And again, now that we have a reasonable value of conductance, we have a much more reasonable flow budget discrepancy there. And so, yeah, so again, if you have a super high value of conductance, you're going to get some flow budget errors, but it's going to be comparable to a specified head boundary condition. You don't normally use it that way. And if you have a really low value of conductance, it kind of disconnects that. It takes so much of a head difference to push water through those sediments between the general head boundary condition and the aquifer that there's almost no impact on the result, very little amount of water going out. And so, yeah, it's kind of fun to play with that and see what impact the conductance has. And so there's a nice little introduction to the general head package in ModFlow.